Okay, so the title of the session is Building Modern Data Pipelines for Streaming Analytics. And what we're going to talk about is how we actually got to streaming 190 billion events per day, or roughly batching 150 terabytes per hour. And of course, we didn't start that at day zero like nobody does. So, how do you get to that point and what are you thinking about? My name is Brian Carpenter, and if you're bored and you want to follow me on Twitter, my name's right there as well. So, our pipeline specifically, there's a lot of different types of pipelines. You can qualify your pipeline any way you want to, but at the end of the day, what we're focusing on is CI/CD. But really, the fundamentals of pipeline management and how you architect and the things you have to do for pipelines, almost no matter what the data type is, they're all kind of the same challenges. It's really just about how you're pushing that data through and how you're doing things like, grabbing source, building, doing functional tests, or it may be something as transforming that data or anything else you're trying to do. But in this case, this is a CI/CD pipeline for our product. So you saw I work for a company called Pure Storage. Specifically, I work on a product called FlashBlade, and our entire CI/CD pipeline for all of the code that we call Purity runs on top of a FlashBlade, and we manage that entire pipeline on our own product. So, eating your own dog food. I think down just south of here, they call it drinking your own champagne. There's a bunch of different ways to say it, but that's what we do there. So this is our own pipeline. And when you look at the beginning of it, right, the whole point is CI/CD works. But when we started, right, we were a startup. So 6 years ago, the product didn't exist, roughly 6 years ago. And so we hired a couple engineers. And after we got from what are we going to build into now we have to build it phase, we had to hire some developers and engineers and things like that. And so we didn't have a ton of people. 10 developers or so, a couple of FlashBlades sitting underneath it. At that time, it was beta hardware even. And, we're only doing hundreds of tests per day, right? We only have one test coordinator, all those kind of things. And we weren't doing a ton of failures. And so just like any automated pipeline you do, you start with what looks like the manual process, which is something as simple as emailing the developer. But over time, that's not sustainable, right? So how do you then automate things like emailing the developer through and validating it was in fact a failure? So you fast forward a little bit and you start to have scale problems. And again, this is still within the first year or so. And you can see we now have over 100 engineers, 1,500 VMs hitting that same platform, and we've now got 250 of our own products that are being tested again and against. Again, this is us trying to break that product, get all the failure logs and all the other things involved with that, and then, of course, test that out. But what we have to do is, you don't really want to have to scale all those QA engineers, right? So the whole point of this is, when an error comes through, do you know it's actually an error? Have you seen it before? Is it real? You want to triage that. So you end up having triage engineers. And the thing about that is, do you want to have hundreds of triage engineers sitting around finding duplicate bugs, finding what's a new one, taking it to the proper developer, all those kind of things? No. So what kind of machine learning can you apply to this pipeline so that you can auto triage and essentially take things, apply it to Jenkins, all the other things involved with that? So that's kind of what we're talking about today. But at the end of the day, this is kind of the the classic, and by the way, this is going to grow and grow and grow, and we'll show you exactly what happened with it. But this is, the log analysis dream, right? And so it is, just build that out there. You want to automate the triaging of failures. You want to extract those performance metrics. You want to save all of the log for future use, right? So this has kind of been said for years. You want to save everything because you don't know what you're going to do. And it's kind of hard because somewhere down there's a budget that says, oh, don't do that. But otherwise, if you could do it in a perfect world, that's what you'd want to do. And then you want to do all of this in a scalable system. Again, if you build for what you know today and don't build for what could possibly come, you end up having to rebuild multiple times, right? And what's the challenge with that? And then the real answer is we want real-time results, and we'll get into those expectations towards the end. So first of all, of course, you've got tons of logs, and you're trying to abstract the value out of them. Is you're going to take a certain set of those logs and you're going to alert and take action, right? Those are the critical ones. That's the first thing you're going to hit. It's the first challenge you're going to take on, but it's a very small set, and you still got all those idle logs. And then, you're going to take some of those logs and you're going to have to do things like ETL. Essentially, you're going to add some sort of structure to it because you're going to take it into another system that's not just a base log. And then you're going to start to aggregate it so that not only is it something you could take action against programmatically, but you can also do things like search against it. And we've done a ton of things since this as well. But you start to evolve that. And then the other thing you want to do is you're going to start to scale each of those systems. So as you perfect, for instance, doing things like taking action, you want to take action against more things. As you perfect your ETL, you want to start to try to scale out that ETL and take it against more things. And of course, you still are going to end up saving more and more data throughout all of that time, because as you're growing, you're creating more data. And as most of the mathematicians, you're all way better at math than I am. You understand that these are not linear problems; these are logarithmic problems a lot of times, right? So they're going to grow at a rate that most people aren't. It doesn't necessarily look like this from a capacity perspective. So let's look at our pipeline. And again, we've got those log sources. That's our products that are booting up, breaking, crashing, and crash dumping, and all the things we do with our products. And so we've got to augment and centralize those. And of course, we've got to store it, right? Very simple. You're all like, yep, that's exactly right. That's a log, and you did store it. Congratulations. But it gets a little harder than that. So at the end, what we're trying to do is we want to aggregate it and visualize it. These are our goals. We want to transform it. We want to put it in a time series database for certain use cases. We want to alert against it, of course, because we want to know what's going on. And we want to apply some logic to those alerts as well. And again, you'll see that this has a logical flow, but at any point you can add a new piece of logic to it. And it's not going to necessarily break down the log pipeline. It's going to break down how you apply the steps in the analysis pipeline. Okay, so first thing we want to do is, how do we index that, right? So how are we solving the problem of indexing it? And then the other thing we're going to see a challenge of is things like adding something like a streaming buffer and a filter. And one of the challenges you see here is you have all this data, and all of a sudden you add a new process, or you want to do something else to it. How do you reprocess all of the existing data that's already in the system, has already gone through the front side of your pipeline, right? So what kind of challenge does that cause if you get into the petabytes or multi-petabytes of that data when you want to do something like re-index, right? So understanding that architecture in of itself is yet another challenge that you want to try to solve. And, so there's that refilter that I was talking about there. And, we come down to storing it. And so, for example, here we had our syslog, and I want to get into that a little bit later because I'll actually show you where, if at any point one of the tools in this system breaks down, you want to be able to change it. So we'll get to there. That's kind of the story at the end of this. And by the way, that our syslog is landing on, conveniently, our own product, which is, again, a massively parallel file system. It does NFS and S3. This isn't necessarily a product pitch, but I want you to understand exactly what we do. And then, we're using Kafka, again, that pub sub architecture, which is, my favorite word right now. I'd like to pub sub breakfast and pub sub a bunch of things, but in this case, we're talking about this architecture for logs. We're going to be able to send that to the filter. And we even see challenges with things like Kafka, not because of Kafka, but really it's because of things like how those logs come in. And when you do a massive dump of logs, do you have consistency on both sides of the pipeline? And we'll show that in a second as well. Okay, so, as we look at some of those other parts, again, as we're doing something like filtering and refiltering, we can apply ETL using something like Spark against that as well, right? So again, that index in the middle there, in this case, the index is actually our file system itself. You may be able to use another thing for indexing. At one time, we were using things like Cassandra for helping with things like that, but it turns out our file system, because of how metadata rich it is, conveniently, we actually use the file system itself as an index, and we'll show you kind of exactly what that means. Now, how do we get the rest of these things as kind of our outcomes? How do we pull them out? Well, good old-fashioned Python, so we just basically built our own tools for how we manage all of those. And then, we visualize it using things like Grafana. We've got InfluxDB in there as well and all those. Now, the pipeline I showed you earlier was not this, right? So we didn't start with almost any of these tools involved, with the exception of FlashBlade itself underneath it from a storage perspective. Over time, as things have scaled, we've had to pull things out, put things in, we've had to add things on, we've had to augment the pipeline and change it from a length or processing perspective. But all the while, the data was able to stay in state on the file system itself, right? Really simplifying how we can change what we're doing dynamically based on the demands of the business. They really like that. So that indexing we're talking about, this is really interesting. Not everybody's going to do something like this, but it's actually, kind of scientifically very interesting. So when we take in raw data, we format it like this, right? So we've got the host, we've got the year, we've got the month, all of these things. Our syslog's producing it, and the consumer is that Spark bash process, right? So the interesting thing is we can now take that index data, it's got its pattern involved with it, and we've got the year and all the other things there. And we're able to use Spark streaming to basically filter or refilter, and then Python comes and picks it up. You saw that in the pipeline, right? So all of this is done on the file system itself. Again, metadata intensive, millions of files in there, no real metadata pressure in there. So we can do those kind of things. It allows us to scan through that file system very quickly. And now we get to querying it, right? So you got an index, you got to be able to go through it. So as we look at querying it, again, we're using basic NFS protocol. For us, this is massively parallel. And it allows you to do things like get very low latency. And so you do something like a list. And if one of the things that we've done is, we'll talk about this here in a second with the NFS client. So you want to do a regular LS. If you've worked with Linux file system tools at all, LS is very slow because it's a serialized process, right? So a lot of people in here have heard something like Moore's Law. The challenge with serialization is actually a different law called Amdahl's Law. And Amdahl's Law is the idea that there's a serialized process anywhere in a massively parallel tool system that ends up being the bottleneck of what you're working on, right? So LS is necessarily slow. So what we had to do is we actually built our own NFS client using libNFS. And that libNFS allows us to go much faster. We're able to parallelize it. And interesting things have happened since we did that. And actually, that's right there. Sorry. We're able to go thousands of times faster than normal LS. Recent releases in the Linux kernel actually now have a parallelization function built into NFS, so they're starting to catch up to those challenges we've been seeing over the last 2 or 3 years. And the good news is those get merged up into upstream. Everybody will be able to take benefit of it, assuming the file system or the architecture supports it. Okay, so back to how this all started, right? So we told you, look at all these things that we've done and how they've gotten there. When you look at the full pipeline when it started, we showed you kind of an early version of it. And here's a middle version of it, right? So at that point, we were doing 20,000 tests a day. At that time, we've got our syslog, Kafka, Spark. We had a little Elastic in there. So again, the indexing and some of the full searches there. Only 1,000 VMs, roughly 170 FlashBlades. Again, storing it all here. We're doing about 6 gigs of data a day. We're doing some custom code there to pick some things up. 6 terabytes of data a day. Right, so we'll skip over this for a second, but you can see this all outputted, by the way, to Jira and Jenkins and all those kind of things, which is very useful. It matures a little bit, and it matures to about 70,000 tests a day, right? So now we're talking 2 or 3 times. And what we're getting to now is about 1 million records a second, right? So we're really starting to put pressure not only on the system, on the logging system. And what we've had to do along the way is we've had to have this infrastructure that can scale dynamically. Again, so all of this in containers, all of this running where, oh, wow, our logging's gone up. We just hired 20 more developers. Logging's going to go up by 10 times. What do we need to do? We better scale up the ingest by 10x, right? So what do we need to do from there? Just really spin up some more containers and start doing that logging, okay? So that was end of July, not this year, by the way. That was a couple of years ago. And that's a picture. That was a picture from the Strata Data Conference a couple of years ago. So now you start to see it, and it gets closer. And this is about as close as it gets to modern day. There we go. And you see where we're now doing about 120,000 tests a day. Okay. Now we're doing, and this is kind of a crazy number here, 2 million records a second. We're doing 24 terabytes of ingest per hour. And you can start to see here we've started to add more and more things on into the architecture kind of dynamically as things needed it. And matter of fact, no offense to our syslog, we were having challenges with our syslog. So we had to write our own log ingester, right? So I wouldn't recommend anybody does that, right? If you can just get it off the shelf, you need to do that. But in our case, we were actually causing problems for ourselves. So we had to create our own log ingester that we then export out into Kafka and a couple other things to do it, simply because during massive crash dumps, we didn't want to lose anything. And so, that was a really interesting challenge for us. That's our core competency, is being able to troubleshoot that. So we had to build it accordingly. So in production, it looks a little bit like this, right? So about a petabyte a month. We're doing 2 million lines a second. We've got 30 branches. We do about 100,000 tests a day. We make about 100 new JIRAs a day. These patterns and fingerprints, these are all things that essentially mean developers are not interrupted, right? So if we know that we've seen it before, we can simply associate it with the existing JIRA and close that and move on, right? So less interruption for your developers. Now you're saying, okay, Brian, you've been talking about yourself this entire time, which is my favorite subject. You've been talking about Pure the entire time, and you've been talking about your CI/CD pipeline. So what else are you trying to tell me? And the answer is we've done it other places. So first of all, we're going to talk about ourselves just a little more. And we also have all of our entire fleet of every device that is at every customer across the globe. And there's 7,000 customers and tens of thousands of devices. Those customers who allow them to call home, they call home all day long. The systems actually open their own tickets. So like 90% of our system, our support tickets are actually created by the systems themselves. We do machine learning against those systems so that we know when a bug occurs. We kind of understand what the firmware levels of the systems are, what's connected to it, all those kind of things. And we could proactively notify the neighbor who also has a very similar configured system and let them know that that bug might occur in their environment so they can do something about it, whether it's a workaround or a fix, right? So we want to take care of our customers. And so our goals is to ingest, manage these requests, do all this live while remaining scalable. So this is our own system and our own company, not the CI/CD pipeline. And the pipeline that powers support, not dissimilar, very similar tools. But again, it's 20 petabytes of raw logs. And all these logs actually start on Amazon itself. And then we use something essentially that looks like a Lambda function and send those home as well. So object on Amazon using a multi-cloud strategy, we might keep 30 days or 60 days or whatever proprietary number we have there, but we have the entire life cycle of all the call home logs at home where we continue to do machine learning and regression and all new models against them on a day-to-day basis. So you're saying, okay, you're still talking about yourself, what else? So we've also done this, again, this is one specific stack, but you can see something like an Elasticsearch stack. And so when something looks like this on Elastic, it's got a bunch of DAS. First of all, when they want to scale it, they have to scale compute and storage. So if you get bound up on something like Lucene, how do you handle being able to scale your storage or your compute without having to buy more storage? And likewise, if you want to have 10 petabytes of Elastic data, but you're not CPU bound, why do you have to keep buying more and more CPU memory? So again, back to that story of disaggregating. If you can disaggregate, and again, this is a massive retailer that's doing this, you can see what they've done from an architectural perspective, and what they've been able to do is simplify, where they can now non-linearly scale compute and storage. So simple keys to remember for now is that you want to, from an indexing perspective, you want to index only what you need and store the rest, right? So, because you're going to come back to it, and you want something that can handle not millions of files. The new number is billion, and that's kind of a low number, right? So you really want to be able to do that. The next thing is you want to optimize for throughput and not latency. A lot of people talk about milliseconds and things like that, but when we're talking about analytics, we're talking about aggregate bandwidth. And I know a lot of people are in here, data scientists. You're not necessarily infrastructure people thinking about even what a bandwidth is, but what you need to be asking for is something that's bandwidth intensive. And when you look at something like a hyperscaler, obviously at their scale, they're not giving you speed, they're giving you bandwidth and throughput. That same experience on-prem. And then disaggregation of compute and storage, I think I've hit that home. Now, when we have these takeaways, so I've shown you a couple of tools, and but the point being is, there's a lot. Actually, there's a few, but there's a lot of good tools. This is Matt Ruck. This is the 2019 version. He has an 18, 17, and 16. You can watch it evolve just like our pipeline evolved. But the point being is, you don't have to memorize this. You won't be able to. You don't have to pick any specific tool. You're going to start with one tool. Something's going to change, and you're going to need to be able to use another tool. Disaggregation supports that. A standard file system, whether it's S3 or NRFS, supports that. The point being is, you want to be able to pick and choose. So for example, not beating up on Docker, but Docker just sold themselves to Mirantis yesterday, right? So you're like, oh, that's a failed strategy. I need to move to XYZ. Great. You need to be able to do that without necessarily having a punishment of having to completely re-architect your environment. Now, you may not react like that, but what if it's something as simple as our first logging tool, we grew out of it. Our second logging tool, we grew out of it. So we had to build our own logging tool. And if we'd had to refactor the entire thing, or even move all those tens of petabytes of data to be able to move them into the new system, it's a huge impact on whether or not you choose to do it, as well as your ability to do it. So you can see where that disaggregation matters when tooling matters. The next thing, you've sort of seen this, not everything scales, right? Which is what I was talking about there, as far as certain tools are not going to meet your needs as you get to a level in your pipeline. And then another thing that's really key here, and this is what we've seen, is that assume all data is bad data. Now this applies to a lot of different parts of machine learning and analytics, but in this case, when it comes to fast data, if you're log ingesting, and let's say you've got 80 million records, and you've got two different systems that are part of a pipeline, and one of them shows 80 million records and the other one shows 96 million records, how do you prove which one actually has the right data? If you have a single source of truth of that data, such as the place where it landed, and then both of them come pick it up from there, 2 of the 3 now are correct and 1's wrong, you know where your problem is, right? So having the ability to see where your problems are in the pipeline and where your data is as you're going that fast and at that scale is very important, especially when you get something like, I don't know which one has the wrong number of logs. And the last one is, all of the change that we're talking about is really to help with agility, right? So this rule's been around for a while, whether it's DevOps, MLOps, data ops, or any of the other ops that are out there. The whole point of all of those is to create agility in your organization so that you can make changes based on what you want, right? So when you have something like a bunch of DAS or a big data lake that doesn't allow you to pick and pull different tools as you need them, or if you have to re-ingest data and do a bunch of things like that, and it causes pain, or even things like patching and patch management because all the data is directly attached and has to hydrate and rehydrate. All of those are challenges in the old way. Now you have 4 copies of that data. With a modern architecture, which is exactly like it's built in the cloud, these are the benefits you get, right? So you can modernize all of that. So that is what we're talking about as far as being able to do a modern data pipeline. Now the question is for you, do you have any questions?